This video discusses another data structure that is commonly used that is called Heaps. A heap is an application of a binary tree. It's a very special binary tree. So a heap must follow two properties. We call them the shape property and the order property. The shape property has to be with the binary tree that we use to store the values. And in the case of a heap, it must be a complete binary tree. You will remember what the definition of complete is from our discussion in the video for binary trees. The order property has to do with the way we're going to store the values into the heap. And there are two possible orderings. One is called the max heap and one is called the min heap. A max heap means two things. One, that the largest value in the entire binary tree, in the entire heap, is located at the root. Take a look at this picture. This is a picture of a heap. 100 is the largest value of all the values that you can see and is located at the root. But more importantly, a max heap means that we need to follow a rule, and the rule says that every parent node must be greater than the values of its children. So if you choose, for example, 19 as a parent node, that means that the value of this node has to be greater than the value of its children, which happens to be 19 is larger than any value here. 36 has a value that is larger than its two children. 17 has a value that is larger than its two children. So we apply the order property recursively when we create the tree and when we add and when we delete. Now, a min heap means that now the value of the root is going to be the smallest of them all. And I need to modify the rule by saying the value of any parent node must be less than the value of its children. I'm going to show you a couple of min heaps in a couple of minutes. Let's talk about the efficiency of heaps in general. So remember, a heap must be always balanced and always complete. And that is a very efficient binary tree. If you remember again the video on binary trees, we discussed the concept of height, and it is the distance from any given node to its root. So the height of this binary tree, of this heap, is 3 because I have 1 level, 2 levels, and 3 levels, which is the distance from 2 to 100. But we also discussed in that video that when we have a complete binary tree, which is the case for a heap, then the height is going to be log base 2 of n. That's the largest value for the height. N is the numbers of nodes. So if I have 10,000 nodes, I figured out what the log base 2 of 10,000 is, and that will tell me what is the maximum height of the tree, which is guaranteed to be a very compact tree. And what that means is that all the operations to insert and delete a node into a heap are going to be of the order of magnitude log base 2 of n. And we know from previous videos that log base 2 of n is pretty efficient. Let's talk about inserting nodes into a heap. To insert a node into a heap, I have to follow two rules. First, I have to maintain the shape property, and then I have to restore the order property. What does it mean to maintain the shape property? Well, a heap is a binary tree that must be complete at all given times. So let's look at this picture. This is a min heap. 1 is the smallest values of them all, and I'm going to insert 3. So where do I insert 3? Well, I have to insert it in a way that I'm going to maintain the shape, which in this case must be a complete binary tree. So there is only one possible way to insert 3, and it is as the right child of A. There is a very simple rule here if you want to figure this out. The rule says that when you insert a node into a heap, what you're going to do is you're going to move from the top level to the lowest level. So I'm looking at the one that has 10, 7, 9, and then I move left to right and I insert the new value in the first left or right child that is available. In this case, the right child of 3. If I were to insert 3 as a child of 5 or a child of 11 or as a child of 10, 7, and 9, then I would be in violation of the shape property because the shape will not be the shape of a complete binary tree. So again, the only option is the right child of 3. Once I do that, I need to restore the order property. Remember, if this is a min heap, the value of any parent must be smaller than the value of its children. Well, look at this subtree. 8 is the parent, is not smaller than 3. So I need to restore the order, and I'm going to do that by swapping 8 and 3. And now I have this subtree, which happens to be a min heap by itself. But now I take a look at this subtree, the one that has a parent with value 4. And again, 4 is not less than 3, so I need to restore the order property, and I swap 3 and 4, and this is what I have. And finally, I'm going to take a look at the entire binary tree, at the entire heap, and then realize that 1 is less than the value of its children, so I don't need to do anything else. I want to insert 8 into this min tree. So what do? I'm going to go top, down, left, right. First place of insertion is the left child of 20. This is a complete tree. This is okay as a heap. But now these two are out of order because I have a min heap. So I need to swap 8 and 20. And then I compare the subtree and I realize that these two are out of order and I need to swap those two. And I'm going to make a final comparison between the 8 and the 5 and realize that those two are in order. So my final binary tree is complete and follows the rules for a heap. So let's talk about removing values from a heap. First, the only value that we remove when we have a heap is the value at the root. It's like a queue. The only value that we remove from the queue is the value at the front of the queue. So similar to a queue in that sense. What rules do we have to follow? The same as before. We're going to maintain first the property that concerns with the shape, and then we're going to restore the order. So let's assume that we have this min tree. So the first value we're going to remove is 4. So now we need to find a new value to put at the root. And the value that we're going to use is the node that is located at the lowest level and the rightmost node, which happens to be 8. So what I do is I delete the node from here and I copy there, I replace it there, and I end up with this heap. So let's see. Does it have the correct shape? The answer is yes, because this is a complete tree. And now I need to restore the order property, because remember, I started with a min tree, so I always must have a min heap or a min tree. So 8 is out of order, so I need to swap it with the smallest of these two values, 6 and 5. I'm going to swap it with 5 and I end up with this. And when I take a look at this heap is a complete binary tree that has or fulfills the order property. Let's use an array representation that is commonly done to represent a heap. It's perfectly okay to use a binary tree, but sometimes we're going to be using an array. There's a special sort called the heap sort. When we discuss heap sort in a different video, you're going to see why it's important to have an array representing the binary tree that is used for the heap. So again, we have a min heap, and the rule to use an array says take the value of the root and put it in index 1. Once you have that, you're going to use these two formulas to decide where the left and the right child of that node should go in the array. So 5 is a left child. Okay, so here it says use this formula, 2 times I. So 3, which is the smallest value of the root, is at index 1. So the I has value 1. So 2 times 1 is 2. So the left child, 5, goes in index 2. On the other hand, the right child, which is 9, where does it go? Again, I is 1. 2 times 1 is 2. Plus 1 gives us 3. So 2 and 3 are the indexes that we use to represent the left and the right child of 9. What do we do next? Now we apply this rule sort of recursively. So we're done inserting the left and the right child of 3. The next node is 5. Now we need to insert the left and the right child of 5. And you will notice that they are right here, 6 and 8. Those are the left and the right child of 5. How do we end up here? Using the same two formulas that I have highlighted, but now the index is 2. So the left child is going to be 2 times 2, which is 4, and the right child is going to be 5. So I'm going to be using the indexes 4 and 5 to store 6 and 8. And indeed, 6 is in index 4, 8 is in index 5. What happened next? Go to 9 and try to figure out where the left and the right child of 9 will go using index 3. We also can use this formula to find the parent. It's very simple. So we can find the parent by performing an integer division of I divided by 2. In other words, if I'm here, index 8 has value 12, and I ask the question, where is the parent of 12? I'm going to use index 8 divided by 2, that gives me 4, and then the answer is going to be that is 6. All right? So indeed, 12 is a child of 6, or 6 is the parent of 12. So I can move back and forth between the array and the binary tree representation to decide where the values go and which one to use. And again, you're going to probably watch a different video called Heap sort that will explain the advantages of using the array representation. Another way to do this, if you have the picture of the heap, we can do it rather quickly by using the following trick. The nodes, the values of the nodes from the heap are stored in the array by performing a level traversal. Level traversal means we're going to go level by level, top down, and then left right. So the first value on the first level, there's only 1. Okay, so 3 goes in index 1. Then left right 5 9 followed by 5 9. Then 6 8 20 10, 6 8 20 10, and finally 12 18 and 9. 12 18 and 9. So I went from the top level, moved down to the bottom level, and for every level I went left to right, and that's the way I store the values. Let's conclude this video by talking about the applications. And one application is that priority queues, which we discussed in a different video, could be represented as a heap, where the priority is going to be the largest value for a max heap or the smallest value for a mini heap. And if you realize now that that's why we remove only the root, because that will be the front of the priority queue. Another common application is a sort called heap sort, so we'll have a different video to discuss heap sort.